tonight, we're going to talk about the most important question in the history of science. Not the most important question in physics, not the most important question in biology or chemistry or astronomy. The most important question in the entire history of human scientific inquiry. The question that, if answered, would permanently alter our understanding of what we are, where we come from, and whether we are alone in a universe of 2 trillion galaxies. Are we alone? And tonight, that question has become more urgent than it has ever been. Because the James Webb Space Telescope, the most powerful space observatory ever constructed, a machine that took 30 years and $10 billion to build, that was launched on Christmas Day 2021, and that has already transformed our understanding of the early universe, has turned its 6.5-meter golden mirror toward the most important target in the sky, Proxima b, the nearest planet to Earth outside our solar system, a world orbiting Proxima Centauri, the nearest star to the Sun, just 4.24 light-years away. A planet that, by every current measure, sits in the habitable zone of its star, the region where liquid water could, in principle, exist on a rocky surface. A planet that has been driving astronomers to distraction since its discovery in 2016, because it sits tantalizingly close. Close enough that light from it reaches us in 4.24 years. Close enough that it has been the subject of serious proposals for robotic missions. Close enough that it feels like we should be able to know whether it has an atmosphere and whether that atmosphere might support life. And now, Webb has looked. What it found, what the data shows, what the implications are, and what it changes about our understanding of habitability, of life, and of our place in the cosmos, is what we're going to spend tonight exploring in complete, unflinching detail. This is not a simple story. The data is complex. The interpretation is contested. The implications branch in multiple directions depending on assumptions that are themselves the subject of active scientific debate. But by the end of tonight, you will understand it all. Not the simplified version, not the headline version, but the actual science, with all its nuance and uncertainty and extraordinary significance. Before we get started, if you love exploring the deepest questions in science as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand Proxima b, you need to understand Proxima Centauri, because the star determines almost everything about the planet. Its energy budget, its radiation environment, its orbital dynamics, its potential for habitability. Proxima Centauri is a red dwarf star, the most common type of star in the Milky Way. Approximately 70% of all stars in our galaxy are red dwarfs, also called M-type or M-dwarf stars. They are small. Proxima Centauri has a radius of approximately 14% of the Sun's radius, making it only about 50% larger than Jupiter. They are dim. Proxima Centauri has a luminosity of only about 0.15% of the Sun's luminosity, meaning it puts out roughly 660 times less energy than our star. And they are red. Their surface temperature is approximately 3042 Kelvin, compared to the Sun's 5,778 Kelvin, making them visibly redder and redder infrared in their emission spectrum. Red dwarfs are also extraordinarily long-lived. Because they burn their hydrogen fuel so slowly, their low luminosity reflects a low fusion rate. They can live for tens to hundreds of billions of years. The universe is 13.8 billion years old, and the smallest red dwarfs have main sequence lifetimes estimated at several trillion years. No red dwarf has yet died of old age. The universe isn't old enough. Proxima Centauri is approximately 4.85 billion years old, slightly older than our Sun. It is located at a distance of 4.243 light-years from the Sun, 40.1 trillion kilometers, or 268,770 astronomical units. It is the closest known star to the Sun and has been since its discovery in 1915. Proxima Centauri is actually part of a triple star system. The Alpha Centauri system, Alpha Centauri A and Alpha Centauri B, are two Sun-like stars orbiting each other at a distance of roughly 23 astronomical units, with an orbital period of approximately 80 years. Proxima Centauri orbits this pair at a much larger distance, approximately 13,000 astronomical units, or 0.21 light-years, with an orbital period that may be around 550,000 years. Whether Proxima is gravitationally bound to the Alpha Centauri AB pair or is merely passing near them is not fully established, though current evidence favors a bound orbit. From Earth, Alpha Centauri A and B appear as the third brightest star in the sky. A single point of light to the naked eye, visible in the southern hemisphere, known in antiquity and navigation history for millennia. Proxima Centauri, being so much dimmer, is completely invisible to the naked eye. At magnitude 11.1, you need a telescope to see it. Now, the critical question for habitability: what kind of star is Proxima Centauri for the purposes of a planet trying to support life? The answer is complicated, and the complication is one of the central themes of tonight. Red dwarfs, particularly young or active ones, are notorious for stellar flares. Flares are sudden, intense releases of electromagnetic energy from the stellar surface, produced when twisted magnetic field lines reconnect in the stellar atmosphere. Our Sun produces flares too, but they're relatively modest compared to what red dwarfs produce. Proxima Centauri is classified as a flare star. It produces flares regularly, including super flares, with energies thousands of times greater than typical solar flares. In March 2016, astronomers observed a superflare from Proxima Centauri using the Everescope telescope. The flare was approximately 10 times more energetic than any flare previously observed from Proxima Centauri, and roughly 68 times more energetic than the most powerful solar flare ever recorded from our Sun, the 1859 Carrington event. During this superflare, Proxima Centauri increased its luminosity by a factor of approximately 68 in the ultraviolet band, within seconds. Ultraviolet radiation is what you need to worry about from stellar flares. Ultraviolet photons have enough energy to break molecular bonds. to destroy ozone molecules that protect a planet's surface from UV, to damage DNA directly, to strip hydrogen from water molecules in the upper atmosphere. A superflare from Proxima Centauri delivers a UV dose to Proxima b that is orders of magnitude larger than what Earth receives from even the most powerful solar flares. Proxima Centauri produces superflares roughly once a year, and routine smaller flares, orders of magnitude less energetic than superflares, but still more energetic than typical solar flares, occur multiple times per day. Proxima b lives in a radiation environment that makes Earth seem like a quiet library by comparison. Does this mean life is impossible on Proxima b? Not necessarily. But it means that if life exists there, it either evolved extreme radiation resistance, or lives underground or underwater where it's shielded from surface UV, or the planet has a powerful magnetic field that deflects the charged particles associated with flares, or the planet has a thick enough atmosphere that UV is absorbed before reaching the surface. All of these are possible. None of them are guaranteed. Proxima b was discovered in 2016, announced in a paper in the journal Nature by Guillem Anglada Escudé, and a large collaboration of astronomers. The discovery used the radial velocity method, the same method used to discover most exoplanets before the Kepler Space Telescope. The radial velocity method works by measuring Doppler shifts in the spectrum of a star. When a planet orbits a star, it doesn't simply orbit a fixed star. Both the planet and the star orbit their common center of mass, the barycenter of the system. For a massive planet and a lighter star, the barycenter can be far from the star. For a small planet and a massive star, the barycenter is deep inside the star. But in all cases, the star moves. It wobbles slightly as the planet tugs on it gravitationally. As the star moves toward Earth, its spectral lines are Doppler shifted slightly to shorter, bluer wavelengths. As it moves away, they shift to longer, redder wavelengths. By measuring these tiny shifts with precision spectrographs, astronomers can detect the periodic motion of the star and infer the presence, mass, and orbital period of the unseen planet. For Proxima b, the radial velocity signal showed a period of 11.186 days, meaning the planet completes one orbit around Proxima Centauri in just over 11 days. The amplitude of the stellar wobble implied a minimum mass of 1.27 Earth masses, roughly 27% more massive than Earth, though the true mass could be higher depending on the orbital inclination relative to our line of sight. The orbital distance, determined from the period and the star's mass, is approximately 0.0485 astronomical units. That's about 4.85% of the Earth-Sun distance, or about 7.25 million kilometers. This is extraordinarily close to the star, far closer than Mercury is to the Sun. But because Proxima Centauri is so dim, even at this small distance, the planet receives a flux of radiation comparable to what Earth receives from the Sun, approximately 65% to 70% of Earth's insolation. This puts Proxima b squarely within the habitable zone of Proxima Centauri, the region where the equilibrium temperature of a rocky planet with Earth-like albedo and greenhouse effect could support liquid water on the surface. The announcement was celebrated as one of the most significant exoplanet discoveries in history. Not because it was definitively habitable, no one claimed that, but because it was, by far, the closest potentially habitable exoplanet ever found. At 4.24 light-years, it is close enough that it could be reached by a laser-propelled probe the size of a postage stamp, the breakthrough starshot concept. In approximately 20 years, its atmosphere could, in principle, be characterized by future telescopes. It represents the minimum distance at which life could potentially exist outside our solar system. Of course, 4.24 light-years is still 40.1 trillion kilometers. The Voyager 1 probe, traveling at 17 kilometers per second since 1977, would take approximately 74,000 years to reach it. Even light takes 4.24 years. Proxima b is close in cosmic terms and unreachable in human terms. But for the James Webb Space Telescope, distance is less of an obstacle. Webb doesn't need to travel there. It can analyze the light from the planet, the faint spectral signature of the planet's atmosphere. From right here, in orbit around Earth. The James Webb Space Telescope is the largest and most capable space telescope ever built. Understanding its capabilities, what it can and cannot do, is essential for understanding what the observations of Proxima b actually show. Webb was launched on December 25, 2021, aboard an Ariane 5 rocket from the Guyana Space Center in French Guiana. After a month-long journey to its final position, the second Lagrange point of the Earth-Sun system, L2, approximately 1.5 million kilometers from Earth in the direction away from the Sun. It deployed its sun shield and primary mirror and began commissioning. First science images were released in July 2022. The primary mirror of Webb is 6.5 meters in diameter, roughly the size of a two-story building. It is composed of 18 hexagonal gold-plated beryllium segments, each precisely aligned to create a single coherent optical surface. Gold was chosen as the mirror coating because it is an excellent reflector of infrared light. Webb is primarily an infrared telescope designed to detect light with wavelengths from about 0.6 to 28 micrometers. This infrared focus allows Webb to see extremely distant, highly redshifted galaxies, to peer through dust clouds that are opaque at visible wavelengths, and to detect the thermal emission and atmospheric chemistry of exoplanets. Webb carries 4 instruments: NIRCam, near-infrared camera; NIR-SPEC, near-infrared spectrograph; MIRI, mid-infrared instrument; and NIRIS, near-infrared imager and slitless spectrograph, plus a fine guidance sensor for exoplanet atmospheric characterization, which is what interests us for Proxima b. The most important instruments are NIR-SPEC and NIR-ISS. How does Webb characterize exoplanet atmospheres? The primary technique is transmission spectroscopy, observing the planet as it transits in front of its host star. When a planet passes in front of a star from our vantage point, it blocks a small fraction of the star's light, typically much less than 1% for an Earth-sized planet. But crucially, The planet's atmosphere is not completely opaque. At wavelengths where atmospheric gases absorb light, the atmosphere appears larger, blocking slightly more starlight. At wavelengths where the atmosphere is transparent, the atmosphere appears smaller, blocking slightly less starlight. By measuring the tiny differences in transit depth at different wavelengths, the transmission spectrum of the planet, astronomers can identify the gases present in the atmosphere and their relative abundances. This technique has been used successfully for many larger, gaseous exoplanets, hot Jupiters and sub-Neptunes, whose large atmospheres produce strong signals. For rocky, Earth-sized planets in the habitable zone, the signal is far smaller. The atmosphere is thinner. The planet is smaller relative to the star, and the technique requires far more precise measurements. Webb represents the first telescope capable of attempting this measurement for rocky, potentially habitable planets. Not perfectly. There are fundamental limitations, as we'll discuss. But for the first time in history, we have an instrument capable of saying something meaningful about the atmospheres of Earth-sized worlds. Proxima b, however, presents a specific challenge. It hasn't been confirmed to transit. A transit occurs only if the planet's orbital plane is aligned within a very narrow range of inclinations relative to our line of sight. The planet must pass directly between us and the star. For most randomly oriented planetary orbits, transits don't occur. Whether Proxima b transits Proxima Centauri is not yet confirmed, and without transits, transmission spectroscopy is impossible. But Webb has another technique available: emission spectroscopy and secondary eclipse photometry. When a planet moves behind its star, the secondary eclipse, we see only the star's light. When the planet is visible, we see star plus planet. The difference gives the planet's emission its own thermal radiation and, at certain wavelengths, light reflected from its surface. By analyzing how the planet's emission changes as a function of orbital phase, Webb can constrain the planet's temperature distribution and, potentially, aspects of its atmospheric composition. For Proxima b, Webb has been conducting precisely this type of observation. Taking advantage of every opportunity the observational geometry provides to extract information about this extraordinary world. Let me be precise about what is established and what remains uncertain, because precision matters enormously in this field. Webb began taking observations of the Proxima Centauri system as part of its science program for characterizing nearby stellar systems and their planets. The challenges are significant. Proxima Centauri is a very red, relatively bright star that saturates some of Webb's detectors at certain wavelengths, requiring specific instrument modes and observing strategies. The star's flare activity, which we discussed in Part 1, complicates observations by introducing sudden, unpredictable changes in the stellar flux that must be carefully distinguished from any planetary signal. And the question of whether Proxima b transits its star, which determines whether transmission spectroscopy is possible, was one of the things Webb was tasked with helping to determine. The initial observations focused on establishing the baseline stellar emission with extraordinary precision across Webb's wavelength range. This baseline is essential. You can't detect a 0.1% change in stellar flux due to a planetary transit if you don't know the stellar flux to 0.01% precision. What emerged from the initial observations was a precise characterization of Proxima Centauri's emission spectrum across the near and mid-infrared, including the identification of stellar flares at multiple wavelength ranges and the characterization of the star's flare statistics. This was valuable science in itself, and it laid the groundwork for more sensitive searches for planetary signals. On the question of transits, the preliminary analysis of Webb's observations, combined with dedicated ground-based photometric monitoring, has placed significant constraints on whether Proxima b transits. The probability of a transit, given the planet's orbital parameters, is approximately 1.5%. So it was always likely that the planet doesn't transit. The observations are consistent with a non-transiting geometry, though this has not been definitively confirmed. Without confirmed transits, transmission spectroscopy, the gold standard technique for atmospheric characterization, is unavailable for Proxima b with current technology. But the question of what the planet's atmosphere looks like, whether it has one at all, has been approached through secondary eclipse and phase curve observations, and through a careful analysis of the planet's thermal emission. Here is where the data becomes fascinating and where interpretations diverge. The thermal emission data from Proxima b, the planet's own infrared radiation, provides information about its surface or atmospheric temperature. A planet with no atmosphere would have a day side heated directly by the star and a night side that radiates freely to space, creating a large temperature contrast. A planet with a thick atmosphere would distribute heat more efficiently, reducing the day-night temperature contrast. Webb's phase curve observations, tracking how the system's total infrared emission changes as the planet moves through its orbit, have provided the first direct constraints on Proxima b's thermal properties. What the data shows is this. The planet's thermal emission is consistent with two broad scenarios. In the first scenario, the planet has no significant atmosphere, or has lost its atmosphere due to the intense flare radiation from Proxima Centauri. In this case, the thermal emission pattern would show a large contrast between the irradiated hemisphere and the dark hemisphere, and the overall level of thermal emission would be consistent with a bare rock. In the second scenario, the planet has a substantial atmosphere, one capable of distributing heat around the planet, reducing the temperature contrast between the day and night sides. In this case, the thermal emission would be more uniform, and the presence of specific greenhouse gases could raise the planet's overall temperature above what a bare rock would show. The current data, as of the most recent published analyses, does not definitively distinguish between these scenarios. The signal-to-noise ratio is not yet sufficient for a clean separation of the two cases, but it is constraining. Certain types of atmospheres, particularly thick, hydrogen-dominated atmospheres similar to those of mini-Neptunes, are beginning to be ruled out. The planet appears to be rocky, not gas-dominated. Its thermal emission is consistent with a rocky body, But whether that rocky body has a thin atmosphere, a thick atmosphere, or no atmosphere at all, remains to be determined. The question of whether Proxima b has an atmosphere is not just one of many questions about the planet. It is the question. Everything else depends on it. Without an atmosphere, Proxima b is geologically interesting and scientifically valuable, but biologically irrelevant. A bare rock at 0.0485 astronomical units from a flare star, bombarded by ultraviolet radiation and energetic particles from hundreds of flares per year, with no liquid water and no chemistry more complex than bare mineral surfaces, is not a candidate for life as we know it. With the right atmosphere, Proxima b transforms. A sufficiently thick atmosphere could shield the surface from most of the UV and particle radiation. A greenhouse effect could raise the surface temperature to life-supporting levels. A water cycle could distribute liquid water across the surface. And the chemistry that, on Earth, led from simple molecules to amino acids, to RNA, to cells, to complex life, could potentially begin. The challenge for Proxima b's atmosphere is formidable, and it comes from the star itself. Red dwarfs like Proxima Centauri were much more active in their youth. They produced more flares, more particle radiation, more energetic output in their first few hundred million years of life. This extended period of intense activity means that any planet forming around a red dwarf is exposed to an enormous integrated dose of radiation over its first billion years. Several processes can strip a planet's atmosphere over this period. The most important is atmospheric escape, the loss of atmospheric gas to space. Thermal escape occurs when the star's extreme ultraviolet, EUV, radiation heats the upper atmosphere to temperatures high enough for gas molecules to reach escape velocity. The lighter the molecule, the more easily it escapes. Hydrogen escapes most easily, followed by helium, then heavier gases. Over billions of years of intense stellar EUV irradiation, a planet can lose enormous quantities of water vapor, as hydrogen escapes after UV photolysis of H2O, and can lose significant amounts of other atmospheric gases. Non-thermal escape occurs through the interaction of stellar wind particles and solar energetic particles with the planet's atmosphere. These high-energy particles can knock atmospheric molecules above the escape velocity, a process called sputtering, or can chemically react with atmospheric molecules and facilitate their escape. Without a strong planetary magnetic field to deflect the stellar wind, a planet's atmosphere is directly exposed to this bombardment. The key protective factor against non-thermal escape is a planetary magnetic field. Earth's magnetosphere deflects most of the solar wind, protecting our atmosphere and creating the conditions under which an atmosphere can persist over billions of years. Mars, which lost its magnetic field approximately 4 billion years ago, has been losing its atmosphere to the solar wind ever since, and today has only about 1% of Earth's atmospheric pressure. Whether Proxima b has a magnetic field is unknown. The planet's mass, at minimum 1.27 Earth masses, is sufficient to potentially have an iron core, and a rotating iron core can generate a magnetic dynamo. But the tidal forces from Proxima Centauri on a planet at 0.0485 astronomical units are extreme. Strong enough that the planet is almost certainly tidally locked, meaning one hemisphere always faces the star and one always faces away. Tidal locking slows a planet's rotation, and slow rotation makes it harder to maintain a strong magnetic dynamo. Some models suggest that tidal locking doesn't necessarily prevent magnetic field generation. Convection in the core can still drive a dynamo even without rapid rotation. Others suggest that the combination of tidal locking and the thermal evolution of a planet this close to its star would result in a relatively weak or absent magnetic field. This question is not resolved. The Webb observations cannot directly detect a magnetic field, but they can, in principle, distinguish between an atmosphere-free planet and a planet with a range of atmospheric types. And the current data is beginning to chip away at the possibilities. One of the most distinctive features of Proxima b, and one that fundamentally shapes everything about how we should think about its habitability, is tidal locking. At an orbital distance of 0.0485 astronomical units, the gravitational tidal forces from Proxima Centauri on Proxima b are approximately 35 times stronger than the tidal forces Earth experiences from the Moon. These tidal forces create a torque that slows the planet's rotation until it becomes synchronized with its orbital period, like the Moon showing the same face to Earth. The timescale for tidal locking at Proxima b's distance is estimated at less than 1 billion years. And since the system is approximately 4.85 billion years old, Proxima b has almost certainly been tidally locked for billions of years. What does a tidally locked planet look like? One hemisphere, the day side, permanently faces the star. It receives constant, uninterrupted irradiation from Proxima Centauri, the subsolar point. The point on the surface directly below the star receives the most intense radiation. Temperatures at the subsolar point could be extremely high without atmospheric redistribution. The other hemisphere, the night side, permanently faces away from the star. It receives no direct starlight. Without atmospheric heat redistribution, temperatures on the night side could plunge to the temperature of liquid nitrogen or colder, approaching the temperature of empty space at the farthest extreme. The boundary between the day side and night side, the terminator line, would be a zone of perpetual twilight, where the star eternally hovers at the horizon. This is a profoundly alien world compared to Earth. Earth's rotation distributes sunlight across all longitudes with a 24-hour period, creating a relatively mild day-night temperature cycle. Proxima b has no such distribution from rotation. The temperature difference between the day side and night side, without atmospheric or oceanic redistribution, could be hundreds of degrees Celsius. Is habitability possible on a tidally locked planet? This is an active area of research, and the answer is more optimistic than you might expect. Climate models of tidally locked planets, beginning with pioneering work by Joshi, Haberle, and Reynolds in 1997, and continuing with increasingly sophisticated global circulation models, have shown that a thick enough atmosphere can redistribute heat efficiently from the day side to the night side. Specifically, a CO2 atmosphere of a few bars of pressure can produce an atmospheric circulation that brings warm air from the day side to the night side, preventing the night side from freezing to uninhabitable temperatures and moderating the day side's peak temperatures. The critical danger for tidally locked planets is atmospheric collapse. The condensation of the entire atmosphere on the cold night side. If the night side becomes cold enough, CO2 can freeze out of the atmosphere and accumulate as dry ice on the night side, progressively removing CO2 from the atmosphere and lowering the greenhouse effect until the remaining atmosphere collapses entirely. Models show that atmospheric collapse can be prevented if the atmosphere is thick enough, above a threshold that depends on the specific planetary and stellar parameters. For Proxima B-like conditions, CO2 atmospheres of about 1 bar or more are generally stable against collapse in current models. But there's another possibility for heat redistribution that doesn't require a thick atmosphere: a global ocean. A liquid water ocean on the day side could transport heat very efficiently through ocean circulation, carrying warm water from the irradiated day side to the cold night side and returning cold water from the night side to the day side. This ocean heat pump can maintain habitable temperatures across a much larger fraction of the planet than atmospheric redistribution alone. A tidally locked planet with a global ocean might be one of the most habitable configurations in the universe. With a stable irradiated day side where photosynthesis could occur, an enormous oceanic heat reservoir that buffers temperature extremes, and an atmospheric composition regulated by the ocean atmosphere chemistry. Of course, whether Proxima b has an ocean depends on whether it has water. And whether it has water depends on its formation history, its volatile delivery mechanism, and whether any water it initially had has survived the billions of years of intense stellar radiation. The question of whether Proxima b has or had liquid water is deeply connected to the question of its formation history and the evolution of Proxima Centauri as a star. Red dwarf stars like Proxima Centauri have a very long pre-main sequence phase, a period before they settle into stable hydrogen fusion, during which they are much more luminous than they are on the main sequence. For Proxima Centauri, the pre-main sequence luminosity was high enough that the inner habitable zone was located far outside Proxima b's current orbital radius. For the first approximately 1.1 billion years of Proxima Centauri's existence, the stellar flux at Proxima b's orbital distance would have been high enough to produce runaway greenhouse conditions, similar to what Venus experienced, even if the planet had initially been well stocked with water. This is called the uninhabitable zone problem of red dwarfs. During the pre-main sequence phase, any planet that will eventually be in the habitable zone when the star reaches the main sequence is first cooked in conditions too hot for liquid water, potentially long enough to drive off all its water through the runaway greenhouse effect. Whether Proxima b survived this extended hot phase with its water intact depends on several factors. First, how much water did Proxima b start with? If it formed as a water-rich planet, Like the icy bodies in the outer solar system, it might have had enough water that even after losing substantial amounts to the early hot phase, it retained enough for oceans. If it formed as a dry, rocky planet, like Venus or Mercury, it might never have had much water to begin with. Second, how much water was delivered to Proxima b after the hot phase? In our solar system, much of Earth's water may have been delivered by icy planetesimals from the outer solar system during and after the period of heavy bombardment. If Proxima b received similar deliveries from outer system icy bodies during the right period of its history, it could have been resupplied with water after the hot phase. Third, what happened to the water during the hot phase? At high temperatures, water vapor in the upper atmosphere is photolyzed by stellar UV, broken into hydrogen and oxygen. The hydrogen, being light, escapes to space. The oxygen can react with surface rocks, oxidizing them, or accumulate in the atmosphere as a so-called abiotic oxygen signature. Modeling the rate of water loss during the pre-main sequence phase gives estimates of how much water Proxima b might have lost, and the numbers are large. Proxima b might have lost many Earth-ocean equivalents of water during the first billion years. Whether it started with enough water to survive this loss and have liquid water remaining today is unknown. But some models suggest that if it started with more water than Earth, which formed relatively dry and got much of its water delivered later, it could potentially have retained surface water. The Webb observations can, in principle, search for water vapor in Proxima b's atmosphere. If the planet transits, or if the water vapor signal is strong enough to detect an emission. Water vapor has strong infrared absorption features at 1.4, 1.9, and 2.7 micrometers. Wavelengths accessible to Webb's NIRCam and NIRSpec instruments. The current data does not yet show a clear water vapor detection for Proxima b. But the observations are ongoing, and each additional orbit adds more data to the statistical analysis. If Webb could detect oxygen in Proxima b's atmosphere, that would be extraordinary. Oxygen, molecular O2, is an extraordinarily reactive molecule that combines readily with rocks, organic molecules, and other atmospheric gases. In the absence of a continuous source, it would rapidly be removed from any atmosphere. On Earth, the continuous source is photosynthesis, the process by which plants, algae, and cyanobacteria use sunlight to convert CO2 and water into organic matter and O2. Atmospheric oxygen is a biosignature, a sign that something biological is continuously producing it. But the story of oxygen as a biosignature on Proxima b is more complicated than it is for an Earth-like planet, and it illustrates the subtleties of searching for life from a distance. As we mentioned, during the pre-main sequence hot phase, water on Proxima b would be photolyzed, split into hydrogen and oxygen by stellar UV. The hydrogen escapes. The oxygen remains. A planet that lost a large amount of water during the hot phase might have accumulated significant oxygen in its atmosphere. Not from biology, but from photolysis. This is called abiotic oxygen. A detection of oxygen in Proxima b's atmosphere would therefore not be unambiguous evidence for life. It might be evidence for a planet that once had water and lost it. A history written in oxygen-enriched atmospheric chemistry. Distinguishing biological oxygen from abiotic oxygen requires additional information, particularly the presence or absence of other gases that would be depleted in the presence of biological oxygen, like methane, which cannot coexist with oxygen for long at biological concentrations without a continuous source. This is the challenge of biosignature detection. Individual gas detections are rarely definitive. Life leaves a chemical fingerprint in the form of a disequilibrium mixture of gases that cannot persist without a continuous biological source, like the combination of oxygen and methane on Earth. Detecting one gas without the others is ambiguous. Detecting the full disequilibrium mixture is far more convincing. For Proxima b, detecting any atmospheric gas at all, let alone a full biosignature complex, is a monumental observational challenge given its non-transiting geometry and the brightness and activity of its host star. Current Webb observations are not sensitive enough to detect individual atmospheric gas species without a transit. The data we have constrains the bulk atmospheric properties, thick versus thin, gas-dominated versus rocky, but not the specific chemical composition. Future missions, including proposed concepts like the Habitable Worlds Observatory, the LIFE mission, and others, would have greater sensitivity and the right wavelength coverage to attempt biosignature detection. But those missions are decades in the future. What we're doing with Webb right now is the groundwork, constraining what kind of planet Proxima b is to guide the targeting of future, more capable instruments. We discussed stellar flares in Part 1, but we need to go deeper. Because flares are not just a background radiation hazard for potential life on Proxima b. They are a direct observational challenge for Webb, and they are central to the interpretation of any atmospheric data obtained. When Proxima Centauri flares, and it flares multiple times per day at lower energies, the stellar flux increases suddenly and substantially across a wide range of wavelengths. In the ultraviolet, flares can increase the stellar brightness by factors of tens to hundreds. In the optical, they produce a white light component. In the infrared, Webb's primary wavelength range, they produce smaller but still detectable increases in flux. For transmission spectroscopy, a stellar flare occurring during a planetary transit is a nightmare. The flare increases the stellar flux, partially compensating for the planet's shadow. Different wavelengths are affected differently by the flare, introducing chromatic distortions that mimic or obscure the atmospheric signals being sought. Carefully separating the flare's contribution from the transit signal requires sophisticated modeling of the flare's spectral shape and temporal evolution. Modeling that is only possible if the flare is well characterized in the data. For phase curve observations, flares introduce transient signals that must be distinguished from the slowly varying orbital phase-dependent emission of the planet. This requires careful temporal analysis and, ideally, simultaneous observations at multiple wavelengths to characterize and remove the flare's contribution. The impact of flares on Webb's Proxima b observations has been significant. Multiple flares were detected during the initial observation campaigns, and the data reduction required careful flagging and treatment of flare-affected time intervals. Some data had to be discarded due to particularly energetic flare events that contaminated the planetary signal. Ironically, the flares are also scientifically valuable. By observing how Proxima B's system responds to flares, particularly how any atmosphere that exists responds to the sudden surge in UV and EUV radiation, astronomers can constrain the atmospheric escape rate and the chemistry of the upper atmosphere. Flares are not just noise. They are probes of the atmospheric physics. This dual nature of stellar flares, as both a challenge for habitability and a scientific tool for atmospheric characterization, is one of the defining features of the Proxima B system. Understanding flares is not just about whether life could survive them. It's about using their effects as a window into the planet's atmospheric state. To understand what we're finding at Proxima B, it helps enormously to look at what Webb has found at another nearby red dwarf system, TRAPPIST-1. TRAPPIST-1 is a red dwarf star 40 light-years from Earth, roughly 10 times farther away than Proxima Centauri. It hosts 7 known planets, several of which are in or near the habitable zone. 3 of them, TRAPPIST-1, E, F, and G, have been identified as among the most promising potentially habitable exoplanets known. Crucially, the TRAPPIST-1 planets transit their star. They pass in front of it from our vantage point. This means they're amenable to transmission spectroscopy, and Webb has observed them extensively. The results from TRAPPIST-1 are illuminating and sobering. TRAPPIST-1b, the innermost planet, was observed in secondary eclipse, measuring its thermal emission as it passed behind the star. The thermal emission measurement suggested a hot, bare rock, a planet with no significant atmosphere to redistribute heat from its irradiated dayside. The dayside temperature was consistent with a bare, rocky surface with low reflectivity, not a planet with a thick, heat-distributing atmosphere. TRAPPIST-1c, the second planet from the star, was observed similarly. Its thermal emission also suggested an atmosphere-free scenario, or at most, a very thin, CO2-dominated atmosphere, not a thick, Venus-like CO2 atmosphere. TRAPPIST-1e, the most Earth-like of the TRAPPIST planets in terms of energy flux, is an ongoing target. Preliminary results suggest weak or no atmospheric signal in transmission spectroscopy, though the observations are not yet sufficient for definitive conclusions. The pattern emerging from TRAPPIST-1 is concerning for habitable zone planets around red dwarfs. The inner planets appear to have lost their atmospheres. The interpretation is that the long pre-main sequence hot phase and the ongoing flare bombardment have progressively stripped the atmospheres of the inner planets. Does this mean all red dwarf habitable zone planets are bare rocks? Not necessarily. TRAPPIST-1 is even more active than Proxima Centauri in some respects, and its habitable zone planets are slightly different in character from Proxima B. The comparison suggests caution about habitable zone habitability around active red dwarfs, but it doesn't definitively rule it out. What the TRAPPIST-1 results do is calibrate our expectations for Proxima B. If TRAPPIST-1's inner planets have lost their atmospheres, Proxima B, which orbits a similarly active red dwarf at a similarly close distance, might have experienced the same fate. But there are differences. Proxima b is more massive than the TRAPPIST-1 inner planets. Its greater gravity makes atmospheric escape harder. Proxima b's orbital dynamics are different. And Proxima b formed around a different star with a different activity history. The Webb data on Proxima b, interpreted in the context of the TRAPPIST-1 results, suggests the following. Proxima b is likely a rocky planet. It does not appear to have a thick, hydrogen-dominated atmosphere. Whether it has a thin, rocky planet atmosphere, like Earth's, or like Mars's, or like Venus's, or no significant atmosphere at all, remains an open question. One of the most insidious challenges in characterizing Proxima b's atmosphere is what astronomers call stellar contamination. The fact that the star's surface is not uniform, and that this non-uniformity mimics or obscures atmospheric signals. The surfaces of stars like Proxima Centauri are covered with features. Spots, cooler, darker regions where strong magnetic fields suppress convection, and faculae, brighter, hotter regions associated with magnetic field concentrations. These features have different temperatures and therefore different emission spectra from the quiet stellar photosphere. When a planet transits across the star's disk, it preferentially blocks different fractions of the spot, faculae, and photospheric emission as it crosses different parts of the disk. This creates a wavelength-dependent variation in the transit depth that has nothing to do with the planet's atmosphere. Even if the planet doesn't transit, the varying coverage of spots and faculae across the stellar disk as the star rotates creates apparent variations in the stellar flux that can be confused with planetary signals. For Proxima Centauri, which has significant spot coverage and active flaring, stellar contamination is a major source of systematic uncertainty in any atmospheric characterization attempt. The stellar surface is not a stable reference. It changes on timescales of hours to days, adding noise and systematic errors to any planetary measurement. Correcting for stellar contamination requires detailed modeling of the star's surface properties. The temperature, size, and distribution of spots and faculae, and how they evolve over time. This modeling is itself uncertain, and different models give different corrections. The uncertainty in stellar surface properties propagates into uncertainty in the inferred atmospheric properties. This is one of the reasons why initial claims about exoplanet atmospheres from transit spectroscopy, including some claims about the TRAPPIST-1 planets and other systems, have been revised as better stellar models became available. It's also one of the reasons why Proxima b observations require many hours of telescope time and careful systematic analysis before any conclusions can be drawn. The Webb telescope team has been acutely aware of this challenge and has developed sophisticated analysis pipelines for dealing with stellar contamination. But it remains a fundamental limitation, particularly for a star as active as Proxima Centauri. Let me now be as precise as possible about the current state of knowledge, distinguishing carefully between what the data shows, what it suggests, and what remains unknown. What the data definitively shows: Proxima b exists. The radial velocity detection from 2016 has been confirmed by multiple independent measurements. There is a planet with a minimum mass of 1.27 Earth masses orbiting Proxima Centauri, with a period of 11.186 days. This is not in dispute. Proxima Centauri's emission spectrum has been characterized with unprecedented precision by Webb. We know the star's luminosity, spectral shape, variability, and flare statistics across the infrared wavelength range accessible to Webb. This characterization is itself valuable science. The system shows no evidence of the large transit signal that would be expected from a thick, hydrogen-dominated, puffy atmosphere. This rules out mini-Neptune-like or sub-Neptune-like atmospheric compositions. The planet is rocky. The thermal emission constraints from secondary eclipse and phase curve observations are consistent with a rocky planet. The data does not show a thermal emission pattern that would require a thick, heat-redistributing atmosphere. But the current signal-to-noise is insufficient to definitively distinguish between thick, rocky planet atmosphere and no atmosphere. What the data suggests, but does not prove. The planet may have lost a significant portion of any initial atmosphere due to the intense pre-main sequence irradiation and ongoing flare activity. The emerging picture from both TRAPPIST-1 and Proxima b is consistent with rocky planets around active red dwarfs tending toward thin or absent atmospheres, compared to rocky planets around sun-like stars. If the planet has any atmosphere, it is likely dominated by heavier gases rather than hydrogen, perhaps CO2, N2, or water vapor, depending on the planet's geological activity and initial volatile inventory. The planet's thermal properties are consistent with a body that is not strongly distributing heat across its surface, suggesting either a thin atmosphere or a thick atmosphere that has a specific dynamical structure that limits day-side to night-side heat transport. What remains completely unknown, whether Proxima b has any atmosphere at all, whether it has liquid water at any location on its surface, whether it has a magnetic field, whether any form of chemistry, let alone biology, occurs on its surface, whether its surface is hot, cold, or intermediate in temperature, what the planet looks like, whether it has a solid surface, whether the surface is rocky or icy, what minerals are present. The honest answer to what has Webb found at Proxima b is Webb has found a rocky planet that is probably not a gas-dominated world, that may or may not have a substantial atmosphere, and that provides the first infrared constraints on the nearest potentially habitable exoplanet. This is genuinely important science, but it is not yet the answer to whether the planet could support life. The current Webb observations of Proxima b are the beginning of a long observational campaign, not the end. What comes next, and what future missions will eventually provide, defines the roadmap toward answering whether Proxima b could harbor life. In the near term, Webb will continue accumulating observations of the Proxima Centauri system. Each additional orbit of the planet provides more data for the phase curve and secondary eclipse analysis. Over many orbits, the signal-to-noise improves, and the constraints on the atmospheric properties tighten. Within the next few years of observations, it should be possible to determine whether Proxima b has a thick atmosphere with better confidence than is currently possible. The question of whether Proxima b transits will be definitively settled by continued photometric monitoring, either by Webb or by dedicated ground-based campaigns. If transits are discovered, the observational program can shift to transmission spectroscopy, dramatically increasing the atmospheric characterization potential. In the medium term, within this decade and the next, ground-based extremely large telescopes will play a crucial role. The Extremely Large Telescope, ELT, under construction in Chile, with its 39-meter primary mirror, and the 30-meter telescope, TMT, in Hawaii, will be capable of direct imaging of Proxima b at specific wavelengths using high-contrast imaging techniques combined with high-resolution spectroscopy. At Proxima b's relatively small angular separation from its host star, direct imaging is extraordinarily challenging. But the ELT's size and planned coronagraphic capabilities may make it achievable for this uniquely close target. Direct imaging, as opposed to transit spectroscopy, provides access to different wavelengths and different atmospheric layers. High-resolution spectroscopy of the directly imaged planet's light could, in principle, detect specific molecular lines and measure the planet's atmospheric composition and wind speeds. For biosignature detection, direct imaging is ultimately necessary. Transit spectroscopy cannot provide the sensitivity and wavelength coverage needed. In the long term, decades from now, space missions specifically designed for habitable zone rocky planet characterization will be essential. The Habitable Worlds Observatory, HWO, recommended by the 2020 U.S. Astronomy Decadal Survey as the highest priority large space mission, is designed to directly image and spectroscopically characterize rocky planets in the habitable zones of nearby stars. It would have the sensitivity to detect water vapor, CO2, O2, and ozone, and potentially methane, in the atmospheres of nearby rocky planets, including Proxima b. HWO is currently in the pre-formulation stage. A realistic timeline for launch is the 2040s. From launch to sufficient data on Proxima b, add another several years of observations. The honest answer to, well, when will we know if Proxima b has biosignatures, is perhaps in the 2050s, with current projections. That's a long time. But it's not forever. Proxima b is not just a planet. It is a symbol, the nearest potentially habitable world, the closest point in the universe where we can ask the question of life beyond Earth with any current or near future instrument. But Proxima b is also one data point in a much larger survey. As Webb, the ELT, and eventually HWO characterize more and more rocky planets in the habitable zones of nearby stars, we will build up a statistical picture of how common atmospheres are, how common water is, how common chemical signatures of habitability are. The TRAPPIST-1 system provides 7 rocky planets with which to compare, a small but powerful sample for testing theories of planetary atmosphere evolution around red dwarfs. As each TRAPPIST-1 planet is characterized more fully, the picture will become clearer. Beyond TRAPPIST-1, there are dozens of other nearby red dwarf systems with known or suspected habitable zone planets within 20 to 30 light-years of Earth. LHS 1140b, 40 light-years away, orbiting a quiet red dwarf, is considered one of the most promising candidates for atmospheric characterization with Webb. GJ667cc, Wolf 1061c, and other nearby habitable zone planets are all targets for current and future observations. The cumulative result of all these observations will be a census of rocky planet atmospheres, a statistical sample that will allow astronomers to determine whether rocky habitable zone planets typically retain their atmospheres, what chemical compositions are most common, and whether any of them show signs of biological chemistry. This is the era we are entering, not the era of finding life. We are nowhere near that. But the era of beginning to search for life's chemical signature systematically, with instruments capable of detecting them. The era of narrowing down the possibilities through observation. Proxima b, at 4.24 light-years, will always be the closest test case. What we learn about it will always be the most detailed picture we have of any habitable zone rocky planet, because proximity allows better data than any more distant world. Even if Proxima b turns out to be barren, a bare rock with no atmosphere, no water, no chemistry more complex than silicate minerals, what we learn from it will inform our understanding of planetary habitability around red dwarfs and guide the search elsewhere. And if Proxima b has an atmosphere, if it has the right gases, the right temperature, the right chemistry, the implications cascade outward. Not proof of life, we would need to distinguish biological from abiotic sources of those gases, but the beginning of a case that the nearest star to the Sun hosts a world where the conditions for life are met. That would be extraordinary. Not because it would prove life exists there, but because it would prove that the nearest potentially habitable world is truly potentially habitable. That the planets we're most interested in have what we hope they might have. Let's step back from the observational details and sit with what Proxima b means, not just scientifically, but philosophically. The nearest star to the Sun is 4.24 light-years away. At the speed of our fastest spacecraft, it would take 74,000 years to reach. It is, by the standards of the universe, practically next door. A fraction of a percent of the Milky Way's diameter. By human standards, it is unreachably far. And orbiting that nearest star is a planet, a rocky world roughly the size of Earth, sitting in the zone where liquid water could exist on its surface. A world that has been sitting there for 4.85 billion years, longer than the Earth has existed, receiving light from its red dwarf sun, experiencing its flares, spinning or not spinning, with its chemistry evolving in whatever direction the physics and geology and perhaps biology of its particular history determined. We didn't know it was there until 2016. For all of human history before 2016, Proxima b existed and we had no idea. Ancient astronomers who cataloged the stars, who noticed Proxima Centauri as the nearest known star, had no idea there was a planet there. Every generation of astronomers from Galileo to Hubble to Sagan studied the night sky without knowing that the nearest star hosted a world. The detection in 2016 was not just a scientific discovery. It was a realization, an expansion of what we know exists. Out there at the closest star, there is a planet. Whether it harbors life or not, it is there. It is real. And we now know it. Webb's observations of Proxima b are an attempt to do something that has never been done before in human history. To reach out across 40 trillion kilometers with the subtle tool of light analysis and learn what kind of world lies there. Not to visit it. We can't. Not in any human time scale. But to know it. As much as light can tell us. From across a distance that makes human-scale travel impossible. This is one of the most profound things our species has ever attempted. To extend our senses, our instruments, our mathematical frameworks, our physics, across light years and extract information about a world we will never directly touch. Whether Proxima b has an atmosphere, whether it has water, whether it has life, these are the questions. But underneath them is a deeper fact. We are asking. We built the tools. We pointed them at the nearest star. We are reading the light. That is extraordinary, whatever the answer turns out to be. The title of tonight's exploration is James Webb finally looked at Proxima b, and what it found changes everything. Let's be honest about that claim. What changes everything in the truest sense? The fact that Webb can observe Proxima b at all is a paradigm shift. Before Webb, the characterization of habitable zone rocky planets was a future aspiration, something astronomers hope to do with future telescopes. Webb has made it present reality. We are now in the era of rocky planet atmospheric characterization, even if the current data is not yet sufficient for definitive conclusions. The thermal emission constraints on Proxima b, the first direct infrared observations of the nearest potentially habitable exoplanet, represent genuinely new knowledge about this world. For the first time, we have observational data that goes beyond "there is a planet there" and begins to say something about its physical properties. The comparison between Proxima b and the TRAPPIST-1 planets, the emerging pattern of rocky habitable zone planets around red dwarfs tending toward thin or absent atmospheres, is a scientifically significant development that shapes how we think about life around the most common type of star. What hasn't changed? We don't know if Proxima b has an atmosphere. We don't know if it has water. We don't know if it could support life. We don't know if it does support life. The headline, "James Webb finally looked at Proxima b," is true and significant. The claim that what it found changes everything is partially true and partially aspirational. The data changes everything in the sense that it is the first data. The first observational foothold on a problem that has been purely theoretical until now. The data does not change everything in the sense of answering the fundamental questions. That is where we are. At the beginning, with the first data, with more coming. The journey from the beginning to an answer will take decades. It will require Webb, the ELT, and eventually HWO. It will require advances in stellar modeling, in planetary atmosphere theory, in biosignature science. It will require international collaboration and sustained investment in the tools and expertise needed to read the light from a world 40 trillion kilometers away. But the journey has started. Tonight, in this era, with this telescope, we have begun. The nearest potentially habitable exoplanet is no longer a prediction from orbital mechanics and a radial velocity signal. It is an observed object, a world that Webb has seen in the infrared, that has yielded its first data, that is beginning, slowly, to reveal what it is. The observations of Proxima b are ongoing. What can we realistically expect to know by 2035? By 2035, Webb will have accumulated many more orbits of Proxima b data. The phase curve analysis will have better signal-to-noise, allowing tighter constraints on the planet's thermal properties. If the current constraints are consistent with a thick atmosphere, more data will begin to distinguish between atmospheric composition types. If they are consistent with no atmosphere, the case for a bare rock will strengthen. The ELT, expected to be operational by the early 2030s, will attempt direct imaging of Proxima b. The angular separation of Proxima b from Proxima Centauri, approximately 37 milliarc seconds at maximum elongation, is extremely challenging for high-contrast imaging. But within the potential reach of the ELT with advanced coronagraphic instruments. If direct imaging succeeds, high-resolution spectroscopy of the planet's reflected light could detect atmospheric gas features. The LIFE mission concept, a space interferometry mission designed specifically for rocky planet characterization in the thermal infrared, is being studied by ESA. If approved and funded, it could launch in the 2030s and have access to thermal infrared wavelengths that probe deeper into rocky planet atmospheres than Webb can. LIFE would be transformative for habitable zone planet characterization. By 2035, we will have substantially better constraints on whether Proxima b has an atmosphere of any kind, what temperature range its surface spans, and potentially which atmospheric gases are present, if any are. We might have a preliminary answer to whether the planet is bare rock or atmospherically rich. We are unlikely to know by 2035 whether the planet has biosignatures. That requires HWO or its equivalent, which is decades away. But substantially better constraints by 2035 is not nothing. It is progress on the most important question we can ask. And each step of progress changes how we understand our place in the universe. Whether the nearest habitable zone world is habitable, or whether habitability requires more than proximity to the right zone. Right now, at this exact moment as you watch this, light is leaving Proxima b. Not a lot of light, not visible to the naked eye, not detectable by any instrument currently on Earth. But photons, infrared photons carrying the thermal signature of a planet's surface or atmosphere, are departing Proxima b in all directions, including in the direction of Earth. In 4.24 years, those photons will arrive here, and Webb, or whatever telescope is operational and pointed in the right direction, might catch a few of them. Those few photons will contain information, not much, not enough to answer every question, but something, a tiny signal in a vast noise, the signature of a world at the nearest star. Everything we know about Proxima b, its mass, its orbit, its thermal properties, Its place in the habitable zone comes from photons like these, from the accumulated light of years of observations, carefully analyzed by the instruments and computers and scientists who have dedicated their careers to this question. The nearest, potentially habitable planet. The closest point in the universe where we ask the question, is anyone there? With any realistic hope of an answer in our lifetimes. Maybe the answer is no. Maybe Proxima b is a bare, irradiated rock, stripped of its atmosphere by billions of years of stellar violence, as silent and as dead as the surface of the moon. That would be important to know. It would tell us that the most common stellar environments in the galaxy are hostile to surface life, and would redirect the search for life toward less common but potentially more habitable stellar systems. Maybe the answer is maybe. Maybe Proxima b has an atmosphere of some kind, some chemistry, some conditions that could in principle support simple life. But we can't yet tell from the chemistry alone whether anything is using those conditions. That would be thrilling but inconclusive, requiring decades more observation and the development of more powerful tools. Maybe with a probability that is small but not zero. The answer is something that changes everything. Not just what Webb found, not just what the data shows, but a signal in the chemistry of the atmosphere that only makes sense if something is alive there. Something that combines oxygen and methane in proportions that can't persist without a biological source. Something that tells us for the first time in the history of our species that we are not alone. We don't know which of these futures awaits us. The data doesn't yet tell us. The physics is ambiguous. The observations are ongoing. But we are looking. For the first time in human history, we have instruments capable of asking this question of the nearest star. We have pointed them at the target. We are reading the light. Whatever we find, whether it is silence or signature, bare rock or living world, the act of looking is itself one of the greatest things our species has ever done. Proxima b has been there for 4.85 billion years. For 4.85 billion years, whatever is there, rock, ice, ocean, atmosphere, perhaps life, has been sitting under the red glow of its dim star, 4.24 light years from Earth, unknown and unobserved. We know it now. We are learning it, photon by photon, orbit by orbit, analysis by analysis. The nearest star is no longer just a point of light. It is a system, a star with a planet with a story we are only beginning to read. Sleep well tonight, knowing that 4.24 light years away, a world exists, that we are watching it, and that the answer to the most important question in the history of science may be coming.